Aurora here with Supercharged Science, Homeschool Science Curriculum for K through 12. And we are going to do a quick 20-minute class in black holes and astronomy. We've been trying to do this for the past 20 minutes, but now I think I got all the bugs worked out. So hopefully this is going to be much more positive experience. So if you like this and you want more, particularly if you want more astronomy lessons, go to my website, www.superchargedscience.com/astronomy. And you'll find a whole host of more science lessons you can do with your homeschoolers, in addition to my best recommendations for telescope and binoculars. And also there's a whole section just in black holes, so if you like today's topic, you can even do more. Okay, so let's get started. Let's just jump straight to what is a black hole. So what is it? Tell me out loud, pretend like I can totally hear you. What is a black hole? Break it down. What is black? It means it doesn't emit or reflect light. Okay, good. And how about a hole? That means that nothing enters, can escape. So anything that crosses the edge is gone forever. It's kind of like a one-way exit door. Okay, so there are a lot of myths out there and a lot of common fears that people have about black holes. And I think it's due to movies and media, honestly. They are not big vacuum cleaners with big infinite-sized bags. They don't just go around like sucking up starships and planets and galaxies and suns and all sorts of things. That's not how they roll. What they do is they're more like, they just sit there with their mouths open and wait for stuff to fall in. If you think of like a basketball hoop, it just sits there, right, waiting for the basketball to come in. It doesn't like chase the players all around the field, right? So black holes are just like that. They just kind of sit there and they're totally cool with whatever comes in. Anything that gets near enough to be under the gravitational influence will slowly get spiraled in and go inward and down into the black hole. And nobody knows what happens once it hits the event horizon. What is their event horizon? Oh, actually, before I tell you that, really put simply, a black hole is an object where, well, here, let me share that ball experience with you. So put out your hand and imagine you've got it like a tennis ball, and kind of throw it up, you catch it, throw it up, catch it, throw it up even higher, catch it, throw it up even higher, catch it, right? Can you imagine being able to throw it so high and so fast that you can escape the Earth's gravitational pull? The answer is yes. If you throw that thing more than 7 miles a second, then that will actually escape and not come back. So you've actually hit a velocity where the Earth's gravity can no longer hold on to it. So this is true for any objects. Any object that has mass is going to have a gravitational field, albeit big or small. Like the sun is huge. You'd have to throw that ball about 400 miles a second in order to escape the sun's gravitational pull. So notice that the objects, as they get bigger, Earth, Sun, even larger than the Sun, that speed, that escape velocity speed goes up. And so what that means is a black hole is an object where in order to escape the gravitational pull, you would actually have to be going faster than faster than the speed of light. So all a black hole is, oh, wrong slide, sorry. Is an object that has an escape velocity greater than that of the speed of light. That's all it is. So a black hole is a place that's so strong that anything like light, when it tries to escape, it gets dragged back, because nothing can travel faster than light. Everything else gets dragged back too. Do you see this picture? This is Niagara Falls. And you see this edge here, right over here? The water that's over here still may have a chance to escape, but once it hits that point of no return, there is no way that water is getting back the same way that it came. So this is called the horizon. It's kind of like the edge of a waterfall. So, whoops, there we go. So a lot of people are worried that black holes will come and like eat them up. And it's a common concern for a lot of people. But there are lots of different ways to detect black holes, and I'm going to share with you a couple of them. So here is my first question to you. If there was an invisible kid in your house right now, how would you find her? What do you think? Give me your best ideas. Pretend I can totally hear you. Just talk to me like I can totally hear you. How would you find this invisible kid? You got 10 seconds. Go. Okay. Would you look for footprints? Cookie crumbs? Maybe the couch cushions are a little bit like indented. Yeah, you'd look for evidence that they were there, right? Okay, so maybe there might be fingerprints on the window, right? Stuff you couldn't normally detect with your eyes, but things that told you that she was there. Black holes we treat the same way. We can detect a black hole by by looking at the way that gravity yanks on things. We can see stars that look like they're orbiting something, but nothing is there. We can't see what the stars are going around, but we know by using math, it can only be something like a black hole. Okay, see these the two stars here? Okay, so if these two were going around just each other, we would expect them to move in a certain way. But the truth is, these appear to like wobble in the sky as they go around each other. So why is that? Okay, before I give you my answer, everybody's like, black hole. Here's something that you can try with your kids at home. So you can take a magnet. If you have like a thin sheet of plastic or cardboard, don't use metal. It's thin sheet of plastic or cardboard, you can actually simulate this. Now magnetism is different than gravity. Just make sure you've got that clear, because magnetism has a north and a south pole. Gravity, as far as we understand it, it's only one way. Okay, but this might be useful to kind of put this into context. So you can put a magnet underneath a thin sheet of cardboard or like poster board, and so with your other hand you can put like a metal ball or a metal object that rolls, or usually like a ball bearing or something works really well. And you're going to pretend that the ball bearing is like a spaceship, and so you're going to put it far away and you're going to roll it slowly across and see if you can figure out where that black hole is. There will be points where you will, if this is your magnet, where the ball will have no effect. There is no influence of this field on the metal ball bearing. There will be times when it actually gets close, but it doesn't get stuck, and other times where it just gets stuck, right? So there's 3 different conditions, and that's true with black holes. Okay, so let's see. Let's go back to our slide. Okay, so this is really similar to how we can detect black holes. It's not by rolling marbles or spaceships towards them, but we can look at the light instead of a spaceship. If the marble is actually a light particle called a photon, this is exactly what gravitational lensing does. I'll talk more about that in a little bit, but we can tell that the light is getting bent. So a black hole is, oh, we already talked about this, a region in space. And we're just skipping around in my presentation here. This is actually just a small part. This is like a 90-minute presentation in astrophysics that a large part of it is black holes. So I'm just giving you some tidbits and just like a smaller, more condensed version of it. So if you like this and you want like the full-blown version, you can get that on my website, www.superchargedscience.com/easy. Like, wow, that was so easy. My kids learned astrophysics and I didn't have to teach it. That kind of easy. Okay, and so let's see. Let me show you another picture of a black hole. Okay, so this is an artist picture. This is how we think it's going to look if we get close to one of these. And the idea here is that the gas and dust that are surrounding and slowly spiraling in, they actually get trapped and then they get heated up because there's a lot of friction going on as they accelerate, as those particles get closer and closer. And so they'll actually start to glow. And so that's why you'll see a ring around black holes. So that's another way that you can actually detect black holes. Now, there's also a shadow that's caused by the bending of light, and it will reveal around a black hole. Now, again, this is an artist picture, so this is about gravitational lensing. I'll show you more about that in just a minute. Now, to image a black hole, you may be thinking, well, how can you have these images, or even begin to think about images of black hole when you can't even see it? You actually need a telescope the size of the Earth. It's kind of like trying to find an apple on the surface of the moon just using your binoculars. You can't do it that way. So what astronomers have done recently, 200 astronomers built the EHT, the Event Horizon Telescope, and they basically set up all these centers around the Earth using special radio telescopes, and they combined all their images so we had an Earth-sized telescope using a bunch of smaller ones put together. And astronomers really recently captured the first image of a black hole. You can actually see the shadow ring that encloses the dark heart of the center of M87. This is a supergiant elliptical galaxy that we can actually see with a backyard telescope, but at the center of that is a huge black hole, and that's the first image that was ever taken using this new technique of an Earth-sized telescope. And remember, black holes don't emit light. So here's a picture of the galaxy. And so this special kind of telescope observes the surroundings of the black hole. The gas that's surrounding the targets actually radiate light. So we're looking in this region, and so they're trying to see if they can figure out the structures that would result the way that the gases would move in a strong gravitational field. And they're thinking, that looks like that might be a black hole there. And so they've got to get really, really clever about how to find it. Now, Cygnus X1 was the first black hole we've ever detected back in the 70s. This is an artist's picture, but this is the way most people think of black holes. Excuse me. This is what we think is happening to Cygnus X1. It's a solar system like ours, but instead of one sun in the middle, there's a huge blue star, much bigger than our sun, and a black hole, and they're going around each other. And the black hole is slowly eating the big blue giant star. So the more things that fall into a black hole, the bigger that black hole will get. It's kind of like feeding a pig. You ever have experience with like pigs? Okay, so you tell me, are pigs neat or are they messy? Yeah, they're messy, right? And do they just eat a little bit, or do they like shove way too much in their mouth? Kind of like kids who are super hungry or really enjoying their food, right? It goes all over the place. So when stuff falls into a black hole, it first swirls around before going in. So if something gets too close, like that ball bearing getting a little too close, it spirals around. Kind of like when you flush the toilet, the stuff swirls around and then before it goes down the hole, same sort of thing. So this makes a black hole, the disk, the material around it, light up like I mentioned before. This is called an accretion disk. The disk will heat up the incoming material, and that's one way we look for a black hole. We look for this glowy disk material. Oh, by the way, stuff just never like falls perfectly straight into a black hole, which like never happens. It usually goes through the accretion disk first. So here's a real picture. What do you think it's a picture of? Don't say a black hole. It's actually something else. Actually, I'm just kidding. It is a black hole, but it looks like a star, doesn't it? Looks like something else. So this is a picture of a black hole that is choking, like I ate too much food. I'm choking. So the black hole is actually, here, let me show you a picture. It tried to eat too much at one time, and so the material started to back up, and a black hole choked, just like what happens with like a pig that was trying to pig out, it chokes. Meaning that the black hole couldn't eat fast enough. But unlike a pig, when the material backs up, it actually goes stellar, which means you've got nuclear reactions going on in that accretion disk. And so we look for things like this. Stars that are not stars. Pretty cool, huh? Okay, there's another way that you can find black holes. Black holes are really messy eaters, like we just mentioned, and usually they try to eat too much at one time. And it has food falling out of its mouth, which will look a whole lot like jets of X-rays coming out into space, straight from the black hole. So if you put your X-ray vision glasses on, particularly your instrumentation if you're a scientist, not your eyeballs, like your computers, and you look for X-rays, usually you'll find a black hole. So, well, not usually, I'd say sometimes you'll find a black hole. This is a picture of high-energy X-ray jet, and a high-energy X-ray jet that is basically light that is being blasted into space. This is actually from a supermassive black hole that is actively feeding. Now remember, when stuff falls in, it just gets lit up around the disk, and sometimes jets shoot out, and that's how we can detect. So if we look for X-rays, we can find them. We look for evidence that they're there, we can find them. Now sometimes one black hole will smack into another black hole. So you can have a black hole all by itself. You can have a star orbiting a black hole like we talked with Cygnus X1, or you can have two black holes that orbit each other. So black holes have a lot of gravity, right? So when those two black holes orbit each other, their masses create what we call gravitational waves that stream through space. Think of like two ducks that are sitting in a pond, and they're bobbing. If you put your hand on one of the ducks and pump it up and down, eventually what happens to the surface of the water? Yeah, it's got these waves, right, that propagate out, and then the other one eventually starts to bob, right? But if the ducks bob themselves up and down, so you can actually have the waves come in and start to interfere with each other. And what happens if you have like a fat duck and a little baby duck, right? Well, they'll give different kinds of waves. So similarly, when we look at things like this, we can actually get information about what kind of duck, what kind of black hole we're dealing with based on the waves that we get. And there's an instrument, the LISA, designed to detect those, which it has. So this image here, you're actually seeing two black holes on the verge of colliding. They're two huge, supermassive black holes, and they show up as little tiny points of light. And they are 3,000 light years apart. So this little space in between, so this is really far away. And what that means is that's a distance, not time, it's like a mile, is a distance. So 3,000 light years, it takes light 3,000 years to go from one to the other. So that's how far apart they are from edge to edge. Okay. Now, astronomers think that what's going to happen is they'll just combine to form an even bigger black hole. So here's a simulation that was done on a computer. Now, this doesn't happen overnight. This takes lots and lots and lots and lots and lots of time in order to happen. Now, I promised to mention something about gravitational lensing. So that'll be the last thing that I talk about here. Now, by the way, if you like this and you want more astronomy lessons like this for your kids, and which include a lot more hands-on projects and activities, you can download my free guidebook from www.superchargedscience.com/astronomy. Isn't that cool? So this is just a simulation based on real physics data of what they think is going to happen when those two collide. Okay, so gravitational lensing. How can you detect a black hole if it's not actively feeding, like material's not falling in, there's no x-rays, there's no accretion disk, it's just kind of there but not active? How do you find it, right? Okay, so when gravity from a black hole bends light, we can actually see the effects in photographs. Now, we can't actually see the black hole, remember, but we can see the light being bent around it. So, for example, this is a real picture that was taken, and it's not as it seems. In this picture, we're actually standing here. Here's the Earth, and we're taking an image of the stars back here, but there's something big in the way. We don't know what it is. So this is the image that was taken, and what's happened is we've actually gotten duplicates. There are 5 images here of the same, it's called a quasar. It's from the same object, and we've gotten 3 images. They don't look the same, but when you look at their signatures, when you look at, kind of break it down and look at the data, they're exactly the same object. Isn't that crazy? So this effect is called gravitational lensing. So the gravitational field of a huge object will bend and amplify around itself. Now, when you see something like this, you know there's something huge between you and what you're looking at. It's like a giant magnifying lens in space that's bending the light. Okay, so here's the stuff, here's what we're imaging, here's the, like the black hole, and instead of going down these straight arrows, it's actually going and being bent. It's kind of like being in one of those funhouse mirror things. So, how was that? Did you guys like that? Okay, so I'm going to pause here for a minute. Now, if you like this and you want more, there's a whole astrophysics lesson with particle physics in there and how to make your own astronomy telescopes. You make refractor and reflector telescopes. And so much more. You can make your own alpha particle detectors. You can actually detect the particles that are charged particles that are zooming through the air right now. And the detector is really cool. It like pings every couple of seconds. 4 or 5 seconds, you'll see like a little ping. Oh, another one. Ping. There's another one. And these particles are invisible. So that's cool. There's a lot of other projects too. I think there's over 200 astronomy projects alone in my online eScience program. Now, for those of you who are new to my online eScience program, it's for K through 12, covers physics, chemistry, biology, life science, you name it, it's in there. Kids will learn how to make robots from junk from the recycling bin, and when they're done, they'll take it apart and make something new. They'll make a laser light show. When they're done with that, they'll make a wind tunnel to test their designs and using your hairdryer and using your Tupperware. And so it's a program that's designed to give you the maximum amount of learning with a minimal amount of materials. So as you notice, I just mentioned a few experiments. There's one experiment I can mention here if you want to do this one. You guys want an experiment? Okay, let me show you. Okay, so one of the questions I often get from kids is, well, if a star is collapsing, it runs out of fuel and it collapses, why does it like go pew and spew everything out? And the answer has to do with, actually, it's a lot easier to explain if I just show you a picture. Okay, you can actually do this experiment like right now. So you have, basically you have 2 balls. and you have like a big ball and a little ball. Now this could be two bouncy balls, it could be a soccer ball and a tennis ball, it could be, but they have to be different sizes, different masses, okay? And so they could be two of any size. And so the idea is you take this ball by itself and you hold it out at arm's length and you just drop it. Don't throw it. And you just drop it. And you notice how high it bounces. It won't bounce all the way up, but it'll bounce, you want one that's like 50 to 80%. Okay? And of the original drop height. And then you bounce the other one all by itself. And you see how high that one goes. Okay? And you do them again, just get a good feel for it. And then you stack them like this picture. And then you release it so it hits the ground still with this little one on top. Okay? And so it's hitting the ground, and then you do that experiment. Actually, you can go do that now if you want. So, what happens? You tell me what happens when you try this. Does the little ball just stay there? It probably rolls off the first 5 times you do this. The result that you're going to see explains why supernovas explode. And so the idea is when the core of a star collapses, it smacks so hard into the core that it rebounds, it bounces back. And as it's rebounding, it's hitting all that incoming material that's still coming in to collapse. And so it rebounds and it hits it like you'll see with this experiment. If you can think about billiard balls, it hits it really hard, and then it'll make a U-turn, turn around, and pew, explode out into space. And so it's a basic experiment in impulse and momentum in physics, and so it's a really cool experiment you can do, again, just with everyday materials. So this idea is just like when the bigger ball is falling, the energy gets transferred to the smaller ball, and so the smaller ball goes pew. By now, hopefully you've tried this experiment. And so the bigger ball, if you watch it during the experiment, before when you just did the big ball by itself, it kind of bounced back up. But when you do it with this experiment, the little one on top, the bigger ball will probably bounce just a tiny bit, if at all. It's because most of its energy, if not all of its energy, is getting transferred to that smaller ball, which you can see by it just explodes off the top. Okay, so basic physics experiments, right? All right, so hopefully this has been helpful. If you like this class and you want more, let me know. I'm Aurora at superchargedscience.com. Don't forget to download your free astronomy guidebook. If you'd like to join me in a class, like right now, if you want to do more astronomy, like right now, you can't wait, you gotta do it, you want to do this whole class, you want to do everything, you want to build the binoculars and the telescopes and the microscopes, you want to do all that stuff, just go to www.superchargedscience.com/easy. Like, wow, that was so easy. My kid's learning and I don't have to teach them. This is fantastic. They're coming back and teaching me science. Wow. You can totally do that as well. There's an informational video there. You can learn about what the program is, what it covers, and see if it's a good fit for your family. It does include a full money-back guarantee. So if you try it and you don't like it, you get a full refund within the first 30 days. So there's nothing to send back. You just try it. If you like it, you stick with it. If you don't, no problem. So I hope you enjoyed this class. I am going to get ready for my next class, and so I will see you guys soon. Take care, everybody.